Okay, I think we can start. Good morning, everyone. So today we're going to continue with the electric field lines, and also I'm hoping to be able to start on the Gauss's law. And I'm going to actually back up and read you one of the examples that we didn't quite finish the last time. But if you have any other questions, I'll be happy to try to answer them before we begin. Is there anything you want me to address before we start? Anything at all? Okay, well, if anything occurs to you, just let me know. Now, the example I want to go back is example 12. So 21, 12. This is the uniformly charged disk, right? So here we had a disk that was of radius, say, capital R, and this is uniformly charged. And we have to find the electric field produced by this field at a point on its symmetry axis, this point P, that is of distance Z from the disk center. Okay. So this was the problem. Now, this is something similar to the other problems that we have looked at, the arc and the straight line, in that we are going to divide this disk into very small pieces, and we're going to calculate the electric field from those pieces, and we're going to add those up. So we are going to be utilizing this formula. The electric field is going to be the integral of this infinitesimal electric field produced by little pieces. But in the first two examples, for the arc and for the line, we were dividing this into like almost point charges. So the electric field produced by those, the E was just dq divided by 4 pi epsilon naught r squared. Okay, so this was magnetic field. In this case, this could still work. We can still do this. We can still take this disk and divide into little point charges, but there's a more practical way. Okay? And that more practical way is to divide this into not little point charges, but into little thin individual disks. So these little rings, not disks. These rings are going to have a radius of r, and their thickness is going to be dr. Now, why do we do this? Now, as long as you can write an expression for the electric field for your charge, then you should use the biggest chunk that you can. Right? That's going to simplify things. So you can just divide this into point charges, but then you need to integrate in two directions. It's a two-dimensional surface. Right? So you need to both integrate in the azimuthal direction, the phi direction, and also in the radial direction. Whereas you already took this integral, we already took the integral in the azimuthal direction, in the angular direction. Right? We solved this example, the electric field of a ring on its symmetry axis. This is already solved. So if you divide this into real rings, consecutive rings, then you're going to be able to take the integral as well. Okay. And because this is already available, it's practical. Sometimes it's not going to be available. Right? Sometimes you would need to, of course, go into little point charges. Like, for example, this is uniformly charged. If it wasn't uniformly charged, if there was some angular dependence for the charge, then you would not be able to use the previous result, because the previous result was for a uniform charge string. Something like that. But if there was some radial dependence for the charge, you could still use it. Right? Each individual little ring would still be uniformly charged, even though the charge density on each ring would be different. Each individual ring would be uniformly charged. So only if there is an angular dependence on the charge, you can't use the formula we already tried. And yeah, this is just for practical purposes. There is no deep reason. So if you can write an expression for the E, you should use the biggest chunk that you can. Typically, that's a point charge, but in this case, it's something different. So here, the expression that we have already tried is 1/4 pi epsilon naught, or you could write Q, of course, Z dq Z squared plus R squared to 3/2. Okay. So this is the distance from the ring center, right? So the ring center, of course, coincides with the disk center. All the rings are going to be concentric. And so this is the same distance that what we have called Z here. This R will be the radius of the ring. And this dq is going to be the charge of the ring. Okay. Now, these Z and R look similar to each other, but they're different. One of them is a variable, the other one is a fixed number. Right? So this R, the radius of the ring, is going to go from 0 to capital R, the radius of the disk. So you start with tiny rings with no radius at all, and then you just enlarge them, and eventually the largest ring you have is going to have the same radius as your disk. So this is a variable. This is going to change. In fact, by changing this R from 0 to capital R, you'll be covering the whole disk. Right? This is how you're going to set up your integral, whereas the Z is fixed. Okay? It looks like a variable because we're using a coordinate name for this, but it's in fact fixed. And in fact, I was designing this problem. I would not call this C. I would call this something else, right? L or some other variable name. Now, as I said, we are going to calculate the electric field due to each small ring or each thin ring, and then we are going to add those up. And in this case, so this is generally true. This, in general, is not true. But in this case, it is true because the individual contribution from all your rings is going to be in the same direction. So the vector sum and the scalar sum give the same thing. There are not different components. They're all pointing upwards along the symmetry axis for all these rings. So I can actually use this one. Okay? I can just add these up. So I only need to calculate this and integrate this. But to do that, I need the charge. So are there any suggestions on how to calculate the charge? I did this last time, but I don't know if you remember. How would you calculate the charge of this individual ring? So they give you that this is uniformly charged, and they give you that its charge density is sigma. This is the surface charge density. Okay? So this is Q divided by A, something like that. The charge per unit area. How would you use this to calculate the charge of an individual ring? To do that, you need the area of the ring, right? Because if you know the area, then by multiplying this charge density by the area, you can actually get the charge of the ring, right? It's a surface density. So surface density times area gives whatever you're seeking. So normally we speak of mass density and we speak of mass volume density, right? So if I told you my volume, if I told you my density, you will be able to calculate my mass. Here, it's a charge density. It's not mass, so you're calculating charge. And it's surface density, so you're not multiplying by volume, but you're multiplying by surface area. This is something, you know, it should become automatic. It should be like something like doing addition, that you shouldn't be actually spending any cognitive effort on this. And that comes with solving problems. You have to solve a few problems, then you will recognize that, okay, I'm given charge density. I can calculate the charge by multiplying by surface area. So what's the surface area? What's the...
Okay, may I say?
Could you speak a bit louder? I can barely hear you.
Okay, may I say yes? If we take disks, then we can take disk and make it as a rectangle.
Mm-hmm.
Rectangle of area 2 pi r, gr. Yeah.
That's right. So these are rings, and I can open them up as strips, right? And the length of the strip is going to be just the circumference of this ring. It's going to be 2 pi r. And the height of the strip is going to be the thickness of the ring. That's just dr. So the surface area, dA, is going to be 2 pi r dr. And multiplying this by dq, multiplying by sigma, I'm going to get dq. Sigma times dA. Okay. So we take this, substitute this in here with this substitution, and I'm going to get, now I need to erase some stuff here. I'm going to get z 2 pi r dr over 4 pi epsilon naught and z squared plus r squared to 3/2. This is my dE. And I can just integrate this out to get my E, because as I said before, all my electric fields produced by all the little rings are going to be in the same direction. So a scalar sum is the same as vector sum. Now, to cover the whole disk, this R, the radius of the little rings, should go from 0 to capital R. And this integral can be done. I think it's done by integration by parts. Right? You call it R square U and something like that. No, sorry, by substitution. And the answer is going to be sigma over 2 epsilon naught times 1 minus z by d squared plus r squared the half. Okay. So if you can't read, don't worry about it. It's already in the book. So there's this sigma over 2 epsilon naught and this 1 minus z over something. Okay. One interesting thing that you can do with this is that you can imagine that you are very close to the surface, or conversely, your disk is very large, right? So this capital R is much larger than this Z. In that case, there's a simplification that takes place. So this, if capital R is much larger than Z, and R squared is much larger than Z squared, I can neglect the Z squared, and this becomes 0. And if that becomes 0, then this 1 minus 0 is just 1. You end up with sigma over 2 epsilon naught. Sorry. So this is for an infinite plane. This is electric field produced by an infinite plane. And perhaps the weirdest thing, most striking thing about this is that it's independent of distance. The Z dependence completely dropped out. It doesn't depend on C. And this might be very surprising, but it's actually, it actually follows from symmetry. It has to be this way because of the properties of the electric field that I'm going to try to demonstrate in a second. Do you have any questions about this example? Okay. Then let's talk a little bit about, yeah. Did someone say something?
Why? Yes. Can you hear me?
Yes, but you need to speak louder.
Okay. In the beginning, why did we put 3/2 on top of z squared plus r squared?
Why did we do that? Why do you think?
Where
did that come from?
I don't know.
Where did that formula come from?
I'm guessing we did Pythagoras theorem, but why is there a cube?
What is this? What am I writing there?
Duyamadım hocam.
What am I writing there? What is this? What is this expression for? What's that dE?
For
dE of what?
d of the disk divided into rings.
dE of the disk divided into rings. What does that mean? This is the electric field of the disk. Okay. What is this dE?
Electric field
Of?
depending on it.
Electric
It's a
field of what?
changing
Electric field of what?
sections. We are dividing
Of the
it
rings.
into.
Electric field of the
Yes.
ring. Okay, of thickness dr and of radius r. This
Yes.
is electric field of such a ring at a distance z from its center along the symmetry axis. So how did I write this down? Where did this come from?
We know the formula of electric
How
field.
do you know the formula? Where did that come from?
I don't really know that.
It's one of the previous examples we solved. It's the example before this in the book.
Okay, yes, but I don't know where it comes from, the root of the formula.
Well, it is in the example. You need to read the example. Did you look at the example?
Yes.
Okay, did you understand how the solution works?
Yes. It
Then
makes sense,
how do
but
you not know the
now
result?
what do you mean?
Well, if you understood the solution, you should understand the result. It just doesn't make sense to me that you understand the solution but not the result. This is the result of the solution given in the book. If you understood the solution, how do you not understand the result?
No, I'm talking about only this example. I didn't understand why there's a 3/2.
Well, it's the result of a derivation. It's not something trivial. It's not doesn't just come out of a hat. You make a calculation, it's the result of the calculation. Were you here? Did you just like follow when I was solving the previous example, the ring? This was the first example we did for a continuous charge distribution. Like all the points are equidistant, so it's simpler.
Yes.
Did you follow that?
Before joining, I read the question.
No, like last week or was it on Monday? We did this example. Were you in that session?
Yes.
Okay, so did you get the electric field, how to calculate electric field of the ring then? So this is the same thing, except it's differential. So electric field for a total charge Q, it's the same expression. This 3/2 doesn't come from anywhere, it comes from a calculation. It's not something obvious. There is a series of calculations you need to carry out, and then this is the result. I don't understand your question, I guess.
I'll look into it again.
Yeah, should. But it's not something trivial. Any other questions?
May I ask a question?
Yeah, go ahead.
This disk is a two-dimensional object, right? Or...
Yes, yes.
Okay.
So it's infinitely thin. We don't consider its thickness. It's thin disk. Anything else?
Hocam, but if it was, if it had a thickness, would it change the answer in
Yes.
some way?
Now, what you would need to do, so if this was like a cylinder, so if it's a thickness, then it's no longer a disk but a cylinder, then you will need to divide this into little thin disks and calculate the electric field of each disk and integrate those. And that will be different for a point on its symmetry axis because the distance of each disk will be different. Right, so there will be the distance of the top disk, and there will be the distance of the bottom disk, and it will just change uniformly from top to the bottom, or from bottom to top. It doesn't matter. Okay? So you need to calculate for each distance the electric field. Right, the electric field depends on that distance, and then integrate that. So it will make a difference. If this is a finite thickness, you will also need to integrate over that variable. Does that make sense?
Yeah, I got it. Thank you.
And perhaps there's an example like that in the book. This will be another situation where the electric field is not just a Coulomb's law, but given by some more complicated expression. So it would be kind of hairy to take that integral. You can still take it, but it's going to be more complicated. Anything else?
May I ask something else?
Yes, go ahead.
There's a rectangle shape in the middle of the whiteboard.
This one?
Yes.
Yeah.
What was that for? Is it the side view of the disk?
So it's the opening of the ring. So we have this disk, right? All this of radius r.
I get it
I'm
now.
dividing this into little individual things. Each has a radius r and thickness dr. You take this, you open this up, you get this rectangular strip.
Oh, okay, I get it now.
Yeah.
Thank you.
Sure. Right. So I'm gonna look at the field lines. So electric field, so far we have been just treating as a vector. So it is some value, some magnitude, and some direction somewhere in space. Right? And to illustrate this, you will need to like draw little arrows all over the space. But there's another way. The so-called field lines that you can use to denote a vector field, which is very practical, and I'm guessing you're already familiar with these, right? So these are just a tool to draw the vector field. You can of course use it for other vector fields as well. It's not restricted to electric field anyway. Now the way you do this is that, let's say that you have a point charge that's positive. What you will do is that you just draw some lines. In this case, they're going to be straight. As you'll see, they don't need to be straight. And please note that I'm not drawing vectors. Okay, the vectors will have their arrows at their tip. I'm just drawing some lines and putting little arrowhead on the lines to indicate their direction. Okay? So this is how you will draw the field lines around the positive charge. For a negative charge, you will draw something very similar, but the arrowheads you use will indicate the opposite direction, like so. Okay. Now these vector field lines have certain properties that are enumerated in your book, so I'm just going to read them. The electric field lines, so this is in section 8 of chapter 21, just near the end. The electric field lines indicate the direction of the electric field. The field points in direction tangent to the field line at any point. And so if I wanted to draw the field vectors here, so it would look perhaps like this over here, maybe a bit shorter over here, even shorter over here, things like that. Okay. Like that at each point. So the electric field lines will be tangent to the, the electric field vectors will be tangent to these field lines at every point. Now, in this case, these are straight lines. So tangent is the same as the line itself. But if they were curved for some reason, then this is they will really be tangent to those curved lines. In fact, if we have like a positive and negative charge like this, so in the close vicinity of the point charges, they would look like that. But as you go from one charge to the other, as you get closer, they would start bending. Okay? And then this bending of the electric field will give you an indication of the direction, the bending of the field lines will give you a direction of the electric field. Yeah, it will of course be like that, going straight and then doing something funny. There's a much better drawing in your figure 34. But the point is the electric field would always be tangent. Now the
Can I ask
second
a question?
property. Yeah, go ahead.
The electric field lines have a direction, and again, it's because of our definition, right? There is not really a direction.
There is a direction, but it is because of our definition. So it is because of our definition, but this doesn't mean that there is no direction. Our definition fixes the orientation, but the direction or the our definition fixes not the orientation, but in which way it points to. So it has to be either this way or this way, okay? But it can't be like this. Okay? So the electric field has a definite direction, but whether it's this way or that way depends on what we choose as positive and negative. Okay? We choose it to be compatible with what we get for the force, and so we don't need to introduce an additional negative sign when we're going from electric field to force. But apart from that, there is no ambiguity. Physically, the electric field line is going to be like this. Whether we put an arrow like that or that is up to us. Okay? That is not fixed by nature, but the shape is fixed by nature. Does that answer your question?
Yes, thank you.
So the second property is that lines are drawn so that the magnitude of the electric field is proportional to the number of lines crossing unit area perpendicular to the lines. The closer the lines, the stronger the field. So the first part of this statement is a little confusing. Don't worry about it too much. But the closer the lines, the stronger the field. Right? This is something you already know. For a point charge, the closer to the point charge, the stronger the field is. And as you see, as we get closer to the point charge, lines are just getting closer. So even if there's no charge distribution, if you're just given the electric field, let's say something like this, Okay, so your field lines, let's say, are like that. You could say that in this region, the left-hand side is a stronger field than the right-hand side because the lines are closer together on the left-hand side and the right-hand side. So by looking at how far the electric field lines are, you can tell how its strength changes. Now, the first part of the statement is making it more accurate by saying that you have to think three-dimensionally. Okay, so here I'm just taking cross-section, like a slice of the three-dimensional electric field lines. Right? So there will also be electric field lines going this way. And if you want to make a quantitative comparison, you really have to look in 3 dimensions, how the lines are getting closer also in this way, not just this way. Okay? So that's what they're saying. So what you need to do is that you need to consider some area and consider the same area over here and count the number of field lines passing through these 2 areas. Okay? If there is more field lines passing through the same area over here and over here, then you have a stronger electric field over there. In fact, if you have twice the electric field, twice the number of field lines passing through this area with respect to this one, then you will say the electric field is twice as strong. Okay? Whereas the individual distance between the lines in a slice that we take like this is not useful quantitatively. Qualitatively, it's still useful. It tells you which one is stronger, but you can't make a quantitative argument. Now, the third statement is electric field lines start on positive charges and end on negative charges, and the number of starting or ending is proportional to the magnitude of the charge. So this is what I tried to draw here. They start on positive charges and they end on negative charges. On top of that, if you're looking at different magnitudes of charges, then you have to adjust the electric field accordingly, right? This follows from Coulomb's law, that the electric field is proportional to the charge, and it follows from the second statement that the field strength is proportional to the number of field lines in a given region. So if you have twice the charge, the electric field is going to be twice as strong, which means it's going to have twice as many field lines. Again, this is not very practical when you're just looking at a slice, but if you're looking at a 3-dimensional picture, then the field lines should really be twice as many. Here, there's a picture again in the same figure, figure 21-34, and they are actually drawing twice as many lines coming out from one of the charges. I don't like that picture too much because it's a 2-dimensional slice from a 3-dimensional thing. It's actually the number of field lines going in every direction that is twice, not just in the slice. Okay, this won't. It's not something I like, but it's just an illustration. Okay. Now there is one thing missing in this statement. They say that the electric field lines originate at the positive charges and terminate at the negative charges. They can also escape and come from infinity. And now imagine in your universe there's just a positive charge. The electric field lines originate in this positive charge. Where do they go? There is no negative charge in your universe, so they can't terminate on a negative charge, but they can escape to infinity. And likewise, if you have a negative charge, then the field lines has to come from infinity and terminate on this one. Okay? So if you have an excess charge in a given situation, you are going to have some electric field lines that doesn't terminate on any charge because there's enough negative charge, or there is going to be some excess field line that's coming from somewhere and terminating on the negative charges because there's not enough positive charge. Right? In that case, you just use infinity. Right? It's just some conceptual thing you need to keep in mind. And then at the end of the statement, they say, also note that the field lines never cross. Why not? Well, this is because of the first property, right? The tangent is going to give the electric field direction, and electric field is a unique vector, right? If they cross, well, there's going to be 2 tangents. You can't tell that. Right? There's going to be a single tangent because there's a unique value, meaning a unique direction and a magnitude for an electric field at a given point in space. So nothing can cross. The electric field lines can never cross each other. Okay? Though in my drawings, sometimes they are going to cross because I make bad.
Can I ask something?
Yeah, go ahead.
Why do we say they're tangents? Like, what is the reason behind it? I'm a bit confused
This is
about
how
that.
you draw them actually. So you have this electric field, drawn as individual vectors, and if you want to go into the field lines, you draw your field line in such a way that all these vectors at a given point on the line is going to be tangent. That's how you draw them. Okay. So let's try to make a more clear picture here. This is too crowded, but I'm just going to draw a single line. So let's say that there's some region of space and you have an electric field line that looks like this. And you want to get what the electric field direction is going to be like. Okay? So then you just go ahead and draw some tangents. So here it's going to look like this. Here it's going to look like this. And here it's going to look like this. Now I'm making the magnitudes up, but the direction of the electric field is going to look like this. Now this is backwards. Okay, this is not how things really work. But more fundamental is the vector representation of the electric field. And you draw your electric field lines in a way that this property is satisfied. Okay? But then it turns out that it's easier to work with electric field lines, and you get so familiar with them that they feel more fundamental. But vectors are in fact more fundamental. They are defined through Coulomb's law in an unambiguous way. So it's just the way field lines are drawn. It's their property. This has a consequence. This is going to allow us to develop Coulomb's Gauss's law, fact, but it's not excellent. And so you want to have a representation of this, vector field in a unique way, and this is one way to do it. There's a mathematical reason behind this. The vector field and the field lines are duals of each other, but that's way too complicated. I don't want to get into that. But if you want to look it up, this is the keyword, duality. Okay. They are just the two sides of the same coin. So.
Anladım hocam, teşekkürler.
All right, now these field lines are easy to work with, certainly in a lot of situations, much easier than the vectors themselves. And we're going to use them to look at how the electric field will behave close to a conductor. Okay. Conductor, and this is going to be my empty space. So remember, our conductors are ideal conductors, and they have charges inside them, and they are free to move. Okay? It's just that because if in the absence of an electric field, the charges are just going to neutralize each other, and there's just it will look like neutral. But if we somehow produce an electric field near or in this conductor, then it's going to separate the charges apart. Okay? And it does this without any delay, just an ideal conductor. Our conductors are ideal. So what will then electric field look like? So I have, let's say, some charges over here. They produce an electric field, and they come and hit the conductor. So if this happens, what would you have on the conductor? I have an electric field line that's coming and terminating on the surface of the conductor. What does this tell you?
Minus of conductor.
Hmm?
Minus sign, minus
Yeah.
charge.
That there has to be a negative charge, because electric field lines always terminate on negative charge, right? So if I have something like this, then I must have some negative charge on the surface of the conductor. Right? In fact, if I bring a positive charge, that is all these field lines coming out of it, then as I bring it over here, as we saw previously, there's going to be some induction of negative charge coming to the surface of the conductor. Right? So this is another way of getting that result. Now, what would be the angle of this electric field with respect to the conductor? So we have these charges that can move freely, and this electric field in general is going to have two components. Right? So there's going to be electric field, let's say, perpendicular, and there's also going to be a tangential component, tangential or parallel component that's parallel to the surface of the conductor. Okay? So they should actually be perpendicular to each other. I should draw this carefully. So something like this. So I have two components of my electric field. Now, I don't have a problem with this one, but can I have a component like this? Would you have a component of the electric field?
I think no, because in static situation, if it's be parallel, it will move. I mean,
But in a static situation, what do you mean by that?
it's symmetry, equal symmetry.
Sorry? But we are assuming that we are at steady state. So if things were moving, they, came to a rest. We don't have dynamics. We have electrostatics. So if that's what you mean by the static situation, yes, the charges are not moving in our situation.
Yes.
We don't have current. Okay. And in that case, if we have an electric field like this, you say that we can't do this because charges would move.
Yes.
Yeah. Will the charges move? Well, they can, right? The electric field
Yes.
is to a force. So these are negative charges that we use there. If there's an electric field, they're going to move opposite. They're going to accelerate opposite the electric field. We can't tell that. We have a static situation, as you put it. We are in state. That's the term I prefer. So we don't have charges moving around. We don't have currents. But if you had a component of the electric field, then this would lead to some force, and that would lead to some motion of the charges. This doesn't happen. Another way to look at this, if I had an electric field like this in a conductor, if I have an electric field this way, then this would have two opposite effects on the positive and negative charges. Right? So this is my electric field. The positive charges will feel a force this way. The negative charges will feel a force this way. Okay? So this is going to lead to some accumulation of negative charges over here and some accumulation of positive charges over here. And what does this do? This produces an electric field. It induces an electric field because of this separation of the charges, and that one cancels this one. Okay? So if you have an electric field that will in fact lead to a separation of charges, the conductor will just cancel it. Now, what about this one? The perpendicular component. Does this not lead to motion? It cannot. The negative charge that we induced would feel a force that's opposite to the electric field, and that's outside the conductor. The charges cannot leave the conductor. Okay, they're restricted to the inside. This is empty space. So this is another one of our assumptions that we can't easily remove the charges from our conductors. To be sure, if you apply a lot of a very strong electric field, you can look polarize the vacuum and things like that, but we're not going to go into that complication. Our charges are restricted to the conductor, and they cannot move perpendicular to the surface. They can only move along the surface. And by moving along the surface, they cancel the parallel component of the electric field, but they can't do anything about the perpendicular component. So the perpendicular component remains, the parallel component disappears. The electric field on the surface of a conductor is always perpendicular to the surface, regardless of the shape. So if the shape is something very complicated, then the electric field is just going to adapt itself, and the charge distribution on the conductor is going to adapt itself to that situation. And this has some consequences that it is discussed in the book, but I think it's better to discuss these in the context of Gauss's law. Okay, now the last thing I want to do in this first session is to look at the motion of charges in an electric field. This is something quite straightforward, but because we now have motion and mechanics, things like that, you can actually come up with some quite complicated problems. But the complication does not arise from electrostatics. Okay? So now I'm going back. Okay? I said that I don't have currents, my charges are in steady state, and so on and so forth. Now I'm going to back up and look at how a charge actually moves under the influence of an electric field. But this is going to be different from the motion of a charge in a conductor. We'll also go back on that. We're going to look at currents and resistors and things like that. But here we just have an individual charge, Q, and there's some electric field around this charge, and that charge is going to, of course, feel a force. And that force is going to be lead to some acceleration. So the acceleration in magnitude is going to be Q E by M. Okay. Now, what does this tell you? Well, if you have an electric field, and if you have two equally charged particles, if their masses are different, their acceleration is going to be different. Here, this is the same situation where you have two masses, you're pushing them, like let's say with two arms, the same force, but one of them is heavier. What does happen? Well, the heavier one accelerates less. The lighter one accelerates more. It's the same deal. Right? You're pushing them with the same force, QE. The heavier one is going to accelerate less. There really isn't anything complicated here, but it's mechanics. And you have already seen that in mechanics, things can get complicated. So usually the complication in these kind of problems doesn't come from this simple calculation, but from the mechanics part. Now, there are two examples in the book, and one of them is two parallel plates that produce some uniform electric field. And there's a little hole in one of the plates, and there's a charge that can just move and go through that hole. So inside this region, inside this between these two parallel plates, there's an electric field. Outside, there's nothing. So inside, there's going to be some acceleration. Right. So what does this mean? Well, your x or the position is going to be given by this. If you choose your starting point as origin, if you start from 0, you just get a displacement that's proportional to the square of the time that's spent. So this is something I'm guessing but if you don't, you have to go back and do this. The other one is again a similar situation, a parallel plate, and we have some uniform electric field, and we have a particle with some velocity, some initial velocity. Now, what does this do? This particle is going to feel an acceleration that's perpendicular to its initial velocity. And you know what happens in this case, right? You've already seen this. What's the situation? What's the common situation for constant acceleration? That's right. Something dropping in a gravitational field. So if you have an initial velocity perpendicular to your acceleration, what do you get? You have a parabola. It's the same thing. You have to be careful here. The force is not necessarily in the direction of the field. If it's a negative charge, it's going to be opposite to the field. Apart from that, there's really no complication. But again, like if you need to think about writing this formula, or if you need to think about writing parabola, solving those, you need to brush up on those, right? Like when you're getting the equation for the parabola, you use the fact that even though the two components of the motion are independent, they have the common time. So tricks like that, you really should be familiar. So, are there any questions about is there anything? I'm kind of acting like this is trivial, but perhaps it's not. Is there anything that I can elaborate more on this motion?
I don't understand the part where on the last example, the electrical lines are going upwards, but if our charge is negative, then it's going to, it wants to go downwards. Then how is that going to work?
That's exactly how it works. So this charge.
Are they just going to cancel each other, or what's going to happen?
No. So the force cannot cancel electric field. There are different quantities. One is like newtons per coulomb, the other one is newtons. So there's no cancellation between those. What's going to happen is that, let's say this is an electron. Okay? In the absence of the electric field, it will feel no force. Right? There's gravity, but forget about gravity. Okay? When you're talking about electrostatic forces, usually they overcome gravity, and unless it's explicitly stated, we should neglect gravity. So if there is an electric field, there is no force acting on it, and it's just going to move in a straight line. So, this way. Now, if there is an electric field, as in here, then it is going to feel a force because of this. Now, an electron has negative charge. So this over here is negative. So these two vectors are going to be the opposite direction. They cannot cancel each other. They are different quantities. They have nothing to do with each other, but they are proportional to each other. In this case, the proportionality constant is negative, so they point in opposite directions. So I'm going to feel a force, or the electron is going to feel a force that's opposite to the electric field. Okay, the force is going to, let me draw this a bit larger. So this is my parallel plate. This is my electric field. And this is my individual electron. The electric field is up, the force is going to be down. Okay. And once you get the force, to get the dynamics, forget about the electric field. The electric field has no more role. You get the force, so force determines the acceleration. Okay. And if you have a velocity like this, and then something that's pulling you down, what kind of motion would you perform? You draw a parabola, like projectile motion. If you throw something, it's just going to follow parabola in a gravitational field, because gravitational field has constant acceleration, and you have a initial velocity that's not parallel to this acceleration. So you get this parabolic shape. The same deal here. There is no cancellation between the electric field or the force, because they're completely different quantities. You can't do that, right? You can't add apples and oranges, so to say. And once you get the force, that completely determines your dynamics. You have your acceleration, you have your initial velocity, you have everything that you need to know to get your orbit. Okay. If this is not clear, you really need to go back and brush up on the first few weeks of
Oh, no, I got it.
dynamics.
And also, are we going to also consider the electrons or the charges weight, mass?
Yeah, they have to have mass. So if you are doing something quantitative, like how long it takes, to cross this and so on and so forth, its mass needs to be given. But when they're asking problems in the book, if they mention it's an electron, they might not explicitly give its mass, because mass of the electron is something you can look up. Okay, an electron is an electron. Its mass is at the back of the book. Sometimes they give it, sometimes they don't, but they don't need to. So here, like in the first example, they give the mass of the electrons, 9.1 times 10 to minus 31 kilograms. But they don't have to. They can just say it's an electron, it's a proton. Mass of the proton is also something known. So yeah, you need to consider mass, because the force is of course fundamental, but you need the acceleration to write down where you are. And to go from force to acceleration, you need the mass.
And also, is there any possible way where the electrical field overcomes the force, and so that the charge or the
Electrical
particle
field leads to force. It doesn't overcome the force. Electrical field is responsible for the force. So if there was no electric field, charges will feel no force. So electric field overcoming force is not meaningful.
that like does not exist? Like we cannot do something like that, right?
Well, if there are additional forces, let's say that I'm pulling an electron by some means, or electrons, that example. Let's say I have a charged object and I'm like pulling it, or it has some mass and it's just being pulled by gravity. And then on top of that, there's an electric field, and the electric field is leading to an additional force, something like this. So I'm not going to say it doesn't exist. It can, but it's a little bit of an artificial example. Typically, if the electrostatic forces play a role, they dominate pretty much everything else. It's very rare that you have an electrostatic force and something else. So what you generally need to do is to consider all sources of electric field, and from the electric field, using the charge, get the force. But artificially, you can create some additional forces. Obviously, there is no limit to this.
Thank you, Hocam.
If you have a concrete example in mind, like something from the book, we can also take a look at that. I don't have anything that comes to my mind.
I was just wondering if can some like a case like that if it can exist, or are we maybe will be held responsible of a case like that or an example like that in the exam or finals or whatever.
But if you encounter that, let me know and we'll look at it. Yeah. I don't recall seeing something like this, but it is possible. It will be a bit artificial. I don't think it's practical, but it's possible. As I said, when you have electrostatic force, if it's significant, it usually dominates. There isn't a situation where it's significant and nearly equal to the other forces in the problem. I can't think of anything in my mind, but you can create something that's possible. Like you artificially put very little charge on an object, and it's just going to float somewhere. There's going to be some equilibrium. And we have been teaching this course for what, 30, 40 years. So there are a lot of problems in the exam. If there are a few that has, situations like this, I will be very surprised. That would be.
Sağ olun hocam.
So let's take a break. Okay. So my time is short.